In this video, we're looking at minimum binary heaps. So what is a minimum binary heap? A binary heap is defined to be a completely binary tree such that all leaves are on at most two adjacent levels. All leaves on the lowest level occur to the left. All levels except for the lowest one are completely filled. The parent node is less than or equal to all its children, and the left and right subtrees are again binary heaps. How do we create a binary minimum heap? So first off, we start off with one element, and one element is always a heap. We are inserting 3 here, and that goes into the first element of the array. To find its children, we do 2 times the index of where it is, and that's the left child. And to find the right child, we do 2 times the index plus 1, and that's going to be the right child. So to add an element to a binary heap, we insert it to the bottom left, which is the second index of the array. Then we compare the child with the parent. If the child is greater, then we just leave it where it is, and if the child is less than the parent, then we swap it. We repeat this process until the first element, until the node that we just inserted is either the first element, which means it's at the top of the heap, or it no longer needs to be swapped with its parents, and then we can say that it's in its proper place. So because 5 is greater than 3, we're just going to keep it where it is. So we're just going to insert 2 now, and that's going to go onto the right-hand side, and that's the third index in the array. Because when we compare 2 with 3, 2 is less than 3, we're going to swap 2, and then it's the top element in the heap, and then we know that our heap is a heap again, and that's where we're going to stop. So now 2 is the top node, and that's swapped with the first index of the array, and it's swapped with 3, and now 3 is the third index, so I've highlighted them in yellow. So now we're going to continue to insert left to right as we're going down this tree, and we're going to insert into the fourth element, the fourth index of the array. Because 4 is going to be less than 5, we're going to swap 4 and 5. So 4 is going to go into the second index, and 5 is going to go into the fourth index of the array. And that's what we see right here, is what I just described as the swapping. And then 4 is going to compare to 2, and it's just going to stay where it is, and then we can say that it's in proper minimum order. Now we're inserting 6, and 6 is going to go into the fifth element of the array. It's going to compare with 4, and it's going to say 4 is less than me, so I'm just going to stay where I am, and then we're going to consider that in minimum binary heap order. So now we're inserting 1 as a child of 3, but on the left side, and that's going into the sixth element of the array. And it's going to compare with its parent, which is 3, and it's going to say that I'm less than 3, so it's going to swap. So now 1 and 3 are swapping, and then now that 1's here, we continue this process, and now 1 is going to compare itself to 2, and then it's going to swap with 2 again also. And then 1's at the top, and we say that's in minimum heap order because that's where it should be. So what's the time complexity? The time complexity is theta of n log n. But why? The actual insertion process, as we see by this proof here, takes log n time. So inserting an element actually takes log n time because it only has to compare to half of the elements every time it swaps with its parents. But because we have to do n insertions and inserting each element as n, we get that n complexity times the log n. So we have to do n insertions at log n time.
Bubble down or heapify. What is a heapify? Heapify is the process of converting a binary tree into a heap data structure. The binary tree has at most 2 child nodes for every parent node except the leaf nodes. The heap is filled from left to right. Heaps must also satisfy the heap order property, which means the value stored at each node is greater than or equal to its children. Here you see an array and a binary heap based on the array. So we have an array with 7 elements with which we build a tree. Our goal is to have a min heap, so to do that we have to heapify or bubble down by comparing the parent and child nodes to see whether they satisfy the heap order property. So to begin the heapifying, we start with the root node. So in this, we compare the child with the parent. So if the child is greater, then we leave it. But if the child is less than the parent, then swap it. So you repeat this process until the element is either the first element or until it does not need to be swapped. So for this, you see in this case, the parent node is 5, the left child is 8, the right child is 3. So the left child node 8 is greater than the parent node 5, so it stays. However, for the right child node, 3 is smaller than 5, so we swap them. So we do the same thing. So now we notice that the root subtree is balanced. So now we go to the left subtree. So in this case, we swap 8 and 4 because 4 is smaller than 8, so we swap it. So now the left subtree is heapified, and now we go to the right subtree. And over here we see that 5 is greater than 1, so we have to swap the 1 and 5. So now the right subtree has been heapified, but now, since we swapped 1 and 5, now we have to look at all the subtrees now. So we observe that in the root subtree, we see that 1 is smaller than 3, so we have to swap them. And now this affects the right subtree as well, so we have to swap 3 and 2. And hence, we finally get our min heap tree by checking all the subtrees. Like we have noticed that the root subtree, the left subtree, and the right subtree have been heapified. So the time complexity for this is, for each bubble down, the time complexity is O log n, but to completely build a heap using bubble down is On. So when heapify is called, the running time depends on how far an element might move down in a tree before the process terminates. In other words, it depends on the height of the element in the heap. In the worst case, the element might go down all the way to the leaf level.
In this section, we will cover examples of when each method is more time efficient. Furthermore, we will discuss and interpret results gathered from timed tests. In regards to heaps, two important terms to differentiate between are swaps and comparisons. Swaps require more steps than comparisons, and in turn have a larger impact on execution time. First, let's analyze bubble down. In most practical cases, bubble down will be more time efficient as it performs fewer swaps when compared to the bubble up. Now suppose we will be utilizing a min heap. The following example shows an array in descending order. This sequence is inherently in max heap order. This allows for a large number of swaps to occur, giving bubble down a smaller execution time. This would yield similar results to using a list in an ascending order in a max heap implementation. Next, let's look at bubble up. There are only a few edge cases where bubble up may be more time efficient. First, we can see that bubble down makes more comparisons than bubble up. Using this knowledge, we can engineer a solution to facilitate a more time-efficient bubble up. The following example consists of an array of equivalent values. This example will require no swaps. In this sense, we are essentially controlling for comparisons. Bubble down requires more comparisons than bubble up. Thus, bubble up should be more time efficient. Lastly, we found consistent differences in our timed executions. With any significant number of swaps, bubble down would become more efficient. When there are no swaps, only comparisons remain. These are small time expenditures. In order to record consistent differences, the array size must be very large. When using a size of 1 billion, the resulting execution time differences will be small but consistent